damping ratio. Okay, now damping ratio, you should be aware of what damping ratio is. It's simply the damping that you've got divided by the damping that would result in critical damping. Now we know that critical damping is when you've got your natural frequency equal to gamma divided by 2. If you remember the equation that we had in the tutorial for omega d, these were different, okay? But obviously if they're the same, you end up with what's known as critical damping. And so by knowing that equation, we can plug that in, you know that the gamma is C upon m, you can plug that in, and omega naught is root k upon m, you can plug that in and it gets the critical damping, which is 2 root mk, okay, and then you can rearrange to get the damping ratio, okay, C divided by 2 root mk. The damping ratio is an important quantity because it will help us, if just by looking at the damping ratio, it helps us know whether our system is damped, underdamped or overdamped, or whether we're at critical damping. If it's under 1, okay, we know we have what's known as underdamping, okay, but if it's over 1, we have overdamped system, okay, and if it's equal to 1, we've got critical damping. So it's quite a quick way to show what sort of damping we've got in the system. The relationship between damping ratio and gamma can be determined by first determining C in terms of gamma. So if we've got our equation for damping ratio, if we rearrange the equation for C, you end up with 2 zeta root mk, okay, and obviously root mk is m to the half, k to the half. And so we can go, therefore, from, we know the gamma is C upon m, so if we stick in what we've got for C at the top here, we've got 2 zeta m to the half, k to the half, over m. Well, m to the half over m is 1 over m to the half, so that's why that drops down. And you can see we've ended up with 2 zeta root k upon m, which is 2 zeta omega naught. And so wherever we saw gamma in that equation, okay, we could replace with 2 zeta omega naught, which is the alternative form. And last week we also covered a term Q, okay, which is the quality of oscillation. If you remember, a low Q meant that we had a high damping, and a high Q meant we had low damping. If you've got a high quality oscillator, then it oscillates very nicely. Okay, so we can again, we know Q we defined last week as omega naught divided by gamma. Again, knowing gamma is C upon m, and you can plug in the same sort of stuff. Well, in fact, you can just plug in this, okay, into here. The omega naughts cancel, you end up with 1 upon 2 zeta. So again, if zeta is high, okay, if you've got a high damping, then Q is correspondingly low. And obviously, if zeta is low, then you've got a correspondingly high Q. Okay. So if you want to relate Q and damping ratio, then this is the equation to use.